Okay, so we've talked about factoring polynomials, and we talked about some special patterns that happen. So just as a review or a reminder, let me show you a couple. The ones we really talked about that we focused on were sum and difference of two cubes. Sum and difference of two cubes. And so what that looked like was if we had two perfect cubes that we were adding, or we could do the subtracting one. And I'll put the subtraction one right here below it. Then we knew that we could factor this. This is where we did little parenthesis, big parenthesis, same change plus. And we did what times itself 3 times gives you the first term, what times itself 3 times gives you the second term. Square it, and multiply them together. Okay, so we did that for the sum. And again, I'm running through this kind of quick because this should just be a review just in case you forgot. Same change plus, we have the A, we have the B, we square the first, square the last, and put them together. Okay, so if you have trouble remembering that pattern, go back and look at the video for sum and difference of two cubes. Okay. Now, in addition to that, and so let me just show you an example also. If we had x cubed, let's actually make it 2x cubed minus, we'll do plus 16. So here, remember, my first step is always, no matter what I'm factoring, I always want to look to see if I can take out a GCF. Okay, GCF meaning a greatest common factor. So I can divide both of these by 2. So I want to take that out and put it on the outside. Now I recognize right off that this is the sum of two cubes because I know 2 to the third power gives me 8. So I set up my parentheses. This 2 stays outside because I factored that out. I do little parenthesis, I do big parenthesis, same change plus. And so now what times itself 3 times gives you x to the third? And that would be x. And what times itself 3 times gives you 8 would be 2. We square it, and we multiply them together to go in the middle. So let me give you one to try just quickly to make sure, just remember, refresh, make sure you remember how to do this. Let's try 3x to the third minus 81. So I hope you've had a chance to work this out. So the first thing I want to do is check for that GCF, and I do know that I can divide them both by 3. It leaves me with x cubed minus 27. So as I look at these, I want to think that 2 to the third is 8, 3 to the third is 27, and I can stop right there because I recognize the 27 is a perfect cube. So go ahead and set up those parentheses. So I got little parenthesis, big parenthesis, same change plus. What times itself 3 times, and what times itself 3 times? Of course, 3 to the third is 27. And we use these to fill in the rest. Squared, together. Okay, so I hope you got that one right. I want to show you, oh, let me remind you, remember we also did a difference of two squares, and the squares are different because they can only be subtraction. Okay, I can't have x squared plus 9, but I could have x minus 9, and so I do the square root of each one of those. Okay, so perfect squares with a minus. So far we've got sum and difference of two cubes, and we've got difference of two squares. And keep in mind, there is no sum of two squares. We can't do it if it's a sum. We can only do it when this middle sign's minus, but the cubes are different. Okay, so on to the new stuff. So there's one more pattern I want to talk to you about, and it's really nothing new for you guys because this is exactly how we have factored already. But what we're going to do is we're going to factor by grouping. I should have said factor by grouping instead of factoring by grouping, but it's okay. So what happens is I have these four terms. Let's say x to the third minus 3x squared minus 16x plus 48. Okay? Notice the four terms here. There's no way for me to factor this like a regular trinomial, like the quadratics we're used to, and it's not a pattern I recognize. So what I'm going to do with these grouping problems is I'm going to do them just like if you think back to how we factored, where we slashed, okay? And I'm going to find the GCF for each of these. So if you think about it, what's the GCF of these two terms? And it's x squared. So if I take an x squared out of those two, it leaves me with 1x minus 3. Always keep that middle sign, and I need a GCF for these two terms. Divide both of these by 16, and it leaves me with x minus 3 again. Okay, so now if you notice, my x minus 3 is exactly the same, so I can take that out and put it out front, and what's left is x squared minus 16, and I got that here. Again, we've done this method. This is how we factored quadratics, so this shouldn't be anything new for you. The only difference is this isn't a quadratic this time. This goes up to a power of 3, but it's the same method, okay? Now remember, we talked about factoring completely. So if you look at the pieces, you ask yourself, can I factor this any further? Well, no, x minus 3 is its own piece. I can't do anything else with that. However, when I get to x squared minus 16, I notice that they're both perfect squares with the minus in the middle, so I have a difference of 2 squares here. So what I want to do is I want to split that up. Now remember, this is not cubes, so it's not the big complicated factor. This one is just the square root of the first minus the square root of the second times, and then I do the same thing but with a plus. Okay, so let me give you one to try here and see if you can get this one. Let's do, we'll say this one's for you to try. X to the third plus 7x squared minus 9x minus 63. So take a minute to try that one. So I hope you've had just a second to give this one a try in factoring. So because I see the four terms, I want to go ahead and slash it. Now what can I take out of these two? Well, I can take out an x squared because this one's got 3 and this one's got 2. It leaves me with x plus 7. And then I look at the second two and I can take out a 9 from those two. So remember, I keep this middle sign, and because that's negative, it's going to change this last sign. So I get x plus 7. Again, I want to take the x plus 7 out front. And it leaves me with x squared minus 9. Now again, I want to look at all these pieces and make sure that I've factored it as completely as I can. X plus 7, I can't factor that down any further, so I write it. But this, another difference of 2 squares, so I get x minus 3 and x plus 3. Okay? Let's see. Let's talk about solving, because we'll get some more practice with this whenever we solve. So I want to take you back to chapter 1 when we solved quadratics. We factored and solved, okay? So maybe we had something like x squared plus 5x plus 6 equals 0, okay? And when we had something like that, there were a couple of things we had to do. We had to make sure that the equation equaled 0, okay? And then what we did was we factored it down. Okay, so that we had it in pieces that were multiplied together to give me that 0. So just looking at this, and just to refresh you a little bit, remember we take A and C and we multiply them together, and we say what two numbers multiply to 6 but add to 5. And so the factors of 6, of course, are 1 and 6 and 2 and 3. So of those numbers, the 2 and 3 are the ones that work. So I get x squared plus 2x plus 3x plus 6. Remember, this time it equals 0. I do have something that it said equal to. So I want to go ahead and slash it. I take the GCF of the first two, which is x. Leaves me with x plus 2. I take the GCF of the last two, which is 3. Again, the middle sign stays the same. It leaves me with x plus 2. And now I take this common factor out of x plus 2. And I'm left with x plus 3. Okay, now the whole point in factoring, remember the first step was make it equal 0, the second step was factor. The third step was to take this factored form and set each piece to 0, right, so that I could actually solve it, because we talked for a while about that zero product property and how if two things multiply together to give you 0, one or more of them must be 0. So set each to 0 and solve. So I know that either x plus 2 is going to be 0 or x plus 3 is going to be 0. And so I solved each one accordingly to get my two answers. So I have -2 and -3. Okay. Now we're going to apply the same concept. Again, this was just review. This is what we did in chapter 1. But I spend so long going over this because it has the same it's the same concept as what we're going to do here. We're going to take all these special patterns that we factored and we're going to add the solving aspect in here, okay? So what I mean by that. Let's take, for instance, let's say I have x to the third plus 7x squared minus 9x minus 63 equals 0, okay? It already equals 0, so that part's kind of done for me, so I don't have to worry about that. Because remember, I want to first make sure that I equal 0. And then I want to factor. So remember your steps in factoring. The steps in factoring in general, I want to look for a GCF to take out of everything. I want to check for a special pattern. So maybe a sum of two cubes, a difference of two cubes, a difference of two squares, or is it a grouping? And if none of those work, then can I group like I can a quadratic? In other words, can I just factor it? Well, if I can spell it right. And I just realized that it did not record any of that. I apologize. So let me run back through real quick so you know what we're doing here. So of course we group together. I have a difference of two squares here whenever I grouped. I took the GCF from the first two and the GCF from the last two. Factored down, took the x plus 7 out. Left me with x squared minus 9. So what I was saying is once we broke up this difference of two squares here, what happens is each piece now goes to 0. And now I have 3 sets of parentheses as opposed to just 2, which is what I'm used to working with, which means I have 3 solutions now instead of 2 solutions. So each one to 0 and then solve each one on its own. So you might need to pause the video a second so you can catch up and copy that since the recorder was not on for that minute there. So let's try one more. Actually, I tell you what, let's have you try one. Let's do Let's do 27t to the third plus 45t squared minus 3t minus 5 equals 0. So I want you to factor and solve that one. Okay, so again, I look for a GCF from everybody, and I don't have one, so I'm going to go ahead and look for a special pattern. The patterns that I know are the sum and difference of two cubes. Definitely can't be that because those only have two pieces. A difference of two squares, and it's again, there's more than two pieces. So now I'm going to check for grouping, and I think I can group this one, so I'm going to try. So when I look at the first two, I can divide those two by, or actually I can take a GCF of 3t squared out of those two, and it's going to leave me with 9t plus, ooh, I can take even bigger out of that, can I? I can actually take a 9t squared out of those two, and this is kind of the process of finding the greatest common instead of just a common. So if I take 9, I can divide 27 by 9 3 times. I can divide 45 by 9 5 times, and I took all the t's away from that one. This sign stays. I can't divide anything by these, so I'm just going to put a 1 outside to hold the place. And again, that last sign changes because the middle sign's minus. So now I have 3t plus 5 leaves me with 9t squared minus 1. Again, it equals 0, and I haven't finished factoring because now I need to look at the pieces that I have and see if I can factor any of those any further. So looking at these, 3t plus 5 doesn't factor any further, so I can just write that one. But 9t squared is a perfect square, as is 1, so that's a difference of two squares. So I can take the square root of each, set them equal to 0. So now each piece goes to 0. I have 3t plus 5 equals 0. I have 3t minus 1 equals 0. And I have 3t plus 1 equals 0. So as I continue solving here, I would subtract 5 and divide by 3. So one solution is negative 5 over 3. And I would add 1 and divide by 3. There's another solution. And I would subtract 1 and divide by 3. And there's another solution. Okay, so just as a recap, you have some special patterns that you need to be aware of. Remember, you have difference of two squares. So this is the one where it can only be subtraction. You have sum or difference of cubes. And then you, of course, have the grouping we just talked about, okay? So the only thing we're really adding on today is the setting equal to 0 and solving portion. I do want to show you one more example that comes up for whatever reason that students struggle with. Let's say I have something that looks like this. 4z to the 5th equals 84z cubed. And I'm asked to solve it. So the first thing I want to do is I want to get everything on the same side and equal to 0. So I'm going to move the 84z to the 3rd. And now I can't combine it with the power of 5 because those aren't like terms, right? So I'll get 4z to the 5th minus 84z cubed equals 0. And now what I want to do is take the GCF out. So I can divide both of them by 4 for sure. This one has 3 z's, this one has 5, so I can take 3 away. Left with z squared minus 21. And so this can't factor down anymore because 21 is not a perfect square. So what I want to do is I want to go ahead and set my pieces to 0. So I've got 4z to the third equals 0, and I've got z squared minus 21 equals 0. Here, if I divide by 4, I got 0, so z equals 0. There's one answer. On this side, if I solve for z, I have to add 21. And now again, we go back to chapter 1. To get rid of this squared, I take the square root. And that gives me two answers. Remember, it gives me plus or minus the square root of 21. Okay? Let me give you one to try, and I will be done. This will be the last example. Let's try, well, let's try 48 p to the fifth equals 27 p cubed. And I'll give you just a second to try that one, and then we'll do it together. All right, I hope you've had a chance to try. So let's go ahead, let's make this equal 0. So to make it equal 0, I'm going to subtract 27p cubed from both sides. So I get 48p to the fifth minus 27p cubed equals 0, because these are gone. And so now I want to say, what can I divide 48 and 27 by? What's the greatest common factor there? I'm thinking it's going to be 3. Let's see what happens when we take 3p to the third out, because we got 5 and 3. I get 16p squared minus 9. Oh, I see a difference of 2 squares here. So 3p to the third. The square root of 16p squared is 4p. The square root of 9 is 3. I get 4p minus 3, 4p plus 3 equals 0. And now everybody goes to 0. And if you solve each one of these, I get 0. If I add 3, and then divide by 4, I get 3/4. Well, it's thinking about it. There we go. Oh, apologies there. I get 3/4. And then on the other side, if I subtract 3 and divide by 4, I get negative 3/4 is my last.